Okay, so when I was asked to give a talk here, I started to think what could be interesting for all of you, and since majority of people here are young people, students, start their adventures in cosmology, so I wanted to start with something very basic. Okay, so let's stop to So I decided to start with Friedmann equations. So this is like a basic thinking in cosmology. And by training, I'm a relativist and working with Einstein equations, with the full Einstein theory. So I decided that maybe it will be interesting for you to, if I will say something about when Friedmann equations, this simplified description of the cosmological model that you have on the right-hand side, is not enough. So we have some properties of the universe that follow from these equations, but to understand them better and to be sure that there are indeed the properties of the physical universe, you have to come back to the full theory to Einstein equations. So this will be the topic of my talk for today. Okay, and this is quite a natural thing, because usually if you want to describe something, it could be some physical system, but it could be universe, then you go to take the theory that is needed to describe that, and then within the theory, you construct a simplified description of the thing, model. Now, as every theory has some application range, so it can be applied to the ground universe in this case, but with some limitations, then the model you construct within the theory has even more restricted application range, because it's based on some simplifications. So all I want to say is that you should use these Friedmann equations with caution. And of course, by going back to the full theory, I do not mean that we want to do some advanced stuff like perturbation theory, structure formation, or other things. No, I will be just talking about those simple Friedmann equations. Okay, so let me start how to go from full theory, how to derive this simplified description. So you need the gravity theory. In this case, we consider Einstein general relativity. So Einstein general relativity is an example, a main example of so-called metric gravity theories. So you know, Einstein had this idea that gravity is not a force. It could be described by the curvature, non-trivial curvature of space-time. So all of us, everything what is going in the universe is happening in space-time. The space-time is a thing that is composed from space and time, so it's like a mixed thing. The points of space-time are events, and then if the curvature of space-time is non-trivial, this means that this is equivalent to some gravity. Okay, and now this is the basic idea. So energy in space-time curves space-time, but you have to provide the field equation. So this is a prescription how this is done exactly. And you can take Einstein equations, but you can modify them or take something like a more general thing in infinite number of ways. But among all the metric theories, Einstein general relativity is distinguished because it's the most simple thing, and it has some properties. I mean, other theories sometimes could be interpreted in terms of this basic approach. And okay, to make a cosmological model, you have to add some simplified assumptions. And when people were doing that, they didn't know much about the universe. So they just came with the most simple thing that can be done if you don't know what is there. So the most simple thing is you assume that the universe is homogeneous and that it's isotropic. Now, it's not trivial. What does it mean that the universe is homogeneous here? Okay, we have to deal with the space-time, but not the space-time is homogeneous, but we have only the spatial homogeneity. So this means that you have to split space-time again into time and space, somehow say that there is something like some cosmic time and the universe at the given instant of this cosmic time. So you don't have to, you shouldn't think about this cosmic time as something very physical. It's just that putting numbers. If you have space-time is made of events, then you have to put some labels to each of the events. And you can put, position in like x, y, and z, and time coordinate. Other way of thinking about that is that you have some observers in the universe and you make a synchronization of the clocks. So you find a way to somehow synchronize the clocks, and then you can ask, for example, one of them or the observer billion years away. It doesn't matter how to do that practically. What was the density at a given time, given day of the universe in this particular place? So when you do this split, then homogeneity just spatial homogeneity indicates that the universe was homogeneous at a given time, where time is this cosmic time function. What I mean by spatial isotropy, it means, again, this is not isotropy of the whole space-time, but isotropy of this, when you do the slicing. So, universe looks the same in every direction, but not just from our place where we are, but we assume that it looks the same for all the places in the universe. Okay, and if you put these two assumptions to the anymetric gravity theory, then you could derive the general form of the metric. Metric is something that describes distances in space-time. And I use this terminology that I use, the general form of the metric, Robertson-Walker metric. But when you assume, in addition, that this metric satisfies those equations, then I call this Friedmann-Robertson-Walker models. So when you put this general form of the metric to the Einstein equations, you get something like this. And here A is a scale factor. So this is a, let's say, single non-trivial function for this class of model. It depends on this depends on the cosmic time. Dot is a time derivative. Rho is the density, it's a function of time as well. Lambda is a cosmological constant and it's constant. K is a parameter that you have one of, without losing generality, you can set it to one of three values. It's -1, 0, 1, but you know all these things. Okay, but now this system, so this is a system of differential equations. Ordinary differential equations is not complete if you do not tell so-called equation, what is the equation of state. So here density, it's not necessary, so we have to give a relation between rho and P, but of course here you can have many different types of, it's a perfect fluid, many different types of fluids. You could have radiation, you could have dust. Some people put the cosmological constant could be put also in the form of perfect fluid. Okay, so this is a basic form of the Friedmann equations. And now, when we think about late universe, or not very early universe, then we more or less know what to put here. Yes? But when we think about early universe, then this is more tricky. I mean, the energies are high, and we don't really know what is the equation of state, what should be put there. Moreover, as you know, there was a process called inflation, so you can supplement the system with the scalar field. The scalar field could be written in the form of the perfect fluid, but it's more tricky. It cannot be interpreted in all cases as a perfect fluid. But, okay, with a losing generality, I will not explicitly include the scalar field here. you may think all of it as a specific form of perfect fluid. I mean, it's not precise, but more or less it works. Okay. And now we have the simplified system, so we can describe the universe. If A is growing, the universe is expanding, and so on. So you can ask about some properties of the universe in this description. And for example, one can easily show, and I will show you this in 2 slides from here, that those equations implies that the universe is not static, so that it have to expand. Of course, you have the static Einstein universe here, but it's unstable, so it's like a special solution. But if you, let's say, if you put lambda equal to 0 and k equal to 0, then this equation becomes very simple. You have square of this a dot over a. It's equal to 8 over 3 pi density. So a density is a positive number, this is energy density. We assume it's positive. Then you have square and something positive on the right-hand side. So the sign of a could be plus or minus, but if we look at observations, then we know the universe is expanding. So the sign is positive. Okay, if you look at this equation here, then with lambda equal to 0, you can put this on the right-hand side. Then if you assume that the rho is positive and pressure is positive, as it happens for standard matter, then you have a minus sign. So in other words, you know from those equations that a dot is bigger than 0 and a with 2 dots, second derivative in time over a is negative. Okay. And if you look just at the scale factor, the a function, as a function of time using those assumptions, then you will find out that there was for this setting there was necessary time where a was equal to 0. And when a was equal to 0, then your metric, there is a problem with your metric, it vanishes. Moreover, you can calculate some things that doesn't depend on the change, on the choice of coordinates. And then you have some blow up of some invariance. So it looks like a problem here. But of course, this is a simplified system, idealization of the real universe. So there is a question if the application range of this thing goes up to this Big Bang or not. And if we can do something to be sure, even if we are not sure if this description is working, to be sure that there was a Big Bang. And that, moreover, the Big Bang was not a failure of this model in the sense of the simplified description, because you can always correct model. Well, you can make it better, more precise, and so on, and maybe there will be no Big Bang. But that we have to be sure that the Big Bang is a problem for the whole theory. So it's something more serious, more problematic, but something that tells you that you need a new physics. That there was a time in the universe that our physics, as we know, doesn't work. We need new physics. So it's this failure of the theory is much stronger than just the failure of the model. Okay. In other words, you cannot trust this analysis at the level of Friedmann equations. You have to be sure that it's not like a specific thing of the symmetry assumptions. Okay. So this is a cat, belongs to my daughter, and as you may have noticed, it's not a real cat, but just a model of a cat. But I show it to you. I mean, there is this joke about spherical chickens in vacuum that the theorists sometimes prove something for spherical chickens in vacuum. The joke goes back to Alan Turing with spherical horses. But this spherical cat is in some sense, is a good model of a cat because you know that it's a cat and it's sufficient for my daughter. So she doesn't have a real cat. But there are like real differences between this cat and the real cat. So one should be careful. So this is similar, this is a simplified description. It's very useful and it's working, but we have to take it with caution. Okay. So So I just show you what I said. This is a scale factor, and I plotted it for a simple model. Maybe I don't know, maybe it was radiation dominated. We are now at this time here, and you know the scale factor is growing. So this function is growing, but the second derivative is negative. So it means that it was growing in earlier times. It was growing faster. So in future it will grow slower. So this curve have to go like this. And then you just draw a curve that is tangent if the Hubble constant will be constant for all the times. And you see that it's necessary this have to cut somewhere zero axis. So it means that there was a time and there was a Big Bang. Okay, but this is a property of the model, and we shouldn't trust it, at least as long as we do not verify this within the full theorem. And so this kind of doubts are somehow natural. So Albert Einstein, as you know, he didn't believe for a long time, longer than other people, that in the expanding universe. He was not convinced. And the first paper finally believed in the expanding universe it was written in 1931, so it's like 4 years later than Lemaitre and other people. So he was reluctant to this idea of the expanding universe. And here I have found that he has some doubts. I mean, in the sense that he was not convinced that the property of the model is the property of the real universe. They had a problem at the time because the cosmological Hubble constant was estimated to be much bigger, so there was a problem with the age of the universe. And he said that maybe the model is not perfect and this treatment is illusory. Okay. But the problem was solved many years later, mainly by this person, and the Nobel Prize was given for that. So it was solved like in 1965, so it was like 50 years after the discovery of general relativity, and he had to wait like 60 years for the Nobel Prize to be recognized for this thing. And you could be surprised that I mentioned Penrose here, because the prize motivation was for the discovery that the black hole formation is a robust prediction of general relativity. And he got the half of the prize. Second half went to astronomers who just showed that we have this black hole really there in the center of our galaxy. And so his job was like to prove a theorem that this is a robust prediction. And the situation for the black hole was, I mentioned that because the situation for the black hole was similar to the situation with the expanding universe. Why? Because in 1939, there was a paper written by Oppenheimer, Snyder, when they showed that in a very simple settings, very simple settings with dust, there is a dynamical solution to Einstein equation that from regular initial data leads to the formation of the black hole. But again, it was like a simplified model. So here in cosmology with isotropy and homogeneity, and then they had the theoretical symmetry and dust. So people were not sure if the black holes really could be formed. And the Penrose showed that this is possible. But of course, to go from Penrose to cosmology and to the problem of the Big Bang I have shown you, you need somebody else. So does anybody recognize this person? It's younger than usually because it's when he did his work. Hawking, yes, it's Stephen Hawking. Because Hawking, the same year, took the idea of Penrose, that Penrose applied to black holes, and he applied it to the universe. And in this thesis, he had a joint paper with Ellis, but in his PhD dissertation, he showed exactly that the universe had the singularity under some assumptions, okay? And that the singularity is not artifact of the simplified description. So, in other words, he took what we have here at the level of the model and showed that this behavior is not under some assumptions, is not artifact of the simplification that we have here, but it's a property of the whole theory. And this is, of course, important because it means that you need new physics at Big Bang. Okay. So how Penrose did it? Of course, Hawking didn't get the Nobel Prize, but it was in some sense fair here because the tools were invented by Roger Penrose. So what Hawking did, he just took a smart mathematical tool and applied it in different situations. So it was like I wouldn't say a trivial contribution, but not so profound as the contribution by Roger Penrose. Okay, so what was this mathematical tool? How to understand that? But before I will show it to you, so you can be explained without using, almost without using, this math that was used by Penrose and Hawking. But we have to think, what is the singularity? And usually, the intuition notion of singularity is if you have some equations, you are doing physics, you try to predict something, or you are doing some calculations in astronomy, and there's something that blows up. So it goes to infinity. So I have a problem because it blows up, and I don't know what to do. My theory doesn't tell me. We believe that infinities are not physical. So if you have infinite density, then you think, oh, okay, something is wrong with the description or with the theorem. But why Einstein was, he was suspicious that maybe there is something wrong with the model? Because singularities are not a new thing. It doesn't just appear in general relativity, but they are known from other theorems. So, for example, if you make something similar to the dust universe, like a cloud of dust in the Newtonian theory, and you keep the perfect spherical symmetry, and you use the dust approximation for matter. So dust approximation means that dust is something that doesn't have pressure, mathematically. We have some dust particles here, and if I would put them together in one place in space, then the real particles will have pressure, yes? I will make a small ball out of the dust in this room. But when I have this mathematical description that we are using in cosmology and that was used here in this Newtonian case, this particle still doesn't feel pressure. But this is mathematical idealization, yes? It's working when they are far away, one from another, but it's not working when I put them together. So my matter model fails, and I have a finite amount of particles in infinitesimally small volume of space, and then I have singularity. So Einstein, he knew that, and because he knew that, he suspected that maybe something like that happened in the relativistic cosmology, yes? Because you use some too simplified model to. In Einstein's gravity, the situation becomes more complicated, because as people recognize that it took them, not all of them, but the community was convinced 50 years later that you could have a coordinate singularities. Because the space-time is curved, then you don't have a preferred, in general, you don't have a preferred system of coordinates, so the whole formalism could be written in the coordinate-independent way. And it's good because you can use whatever coordinates are correct, but sometimes the coordinates just fails to describe the manifold, and then you have a singularity blow up something, but only because of the problem with coordinates, not a physical singularity. And then if you have a blow up of something, then space-time is defined as Lorentzian manifold, and Lorentzian means that it's a manifold equipped with Lorentzian metric. And if the metric blows up, then you don't have metric, so it's not a part of space-time. So singularities do not belong to space-time, and everything we describe belongs to space-time. in our theory. So this is like an additional obstacle to understand that. So people try to understand that using invariance. So you get rid of this dependence on the coordinate, on the choice of coordinates. And this is partially working, but it turns out again that relativity is tricky. So you could have spacetime that are singular in the sense that you cannot find non-singular description of the curvature there, but all invariants, so these quantities that do not depend on the choice of coordinates are fine. Okay? So it's like more problematic things. So finally people decided that the best description of the singularity is geodesic incompleteness. What do they mean by that? When you have space-time, you have some test bodies moving in the space-time. So like you have the sun and the astronaut, or Earth and the astronaut. So astronaut is much more smaller than the Earth. So you can treat him as a test particle. And this means that he curves space-time, but you think, I mean, this is so small. Additional curvature because of that you could neglect that. So in fact, when you have a space-time, it would be static, stationary, or dynamical space-time. You can use geodesic equations to find how free particles, observers, or whatever is moving in the space-time. And now it could happen that at some point, your description fails. So for example, you have, I don't know, this astronaut, and you want to know where he is not using any jetpack, and he's just flying through the space. You want to know where he will be in 2 hours. You try to calculate that, but then you come to a point that something is wrong and you cannot continue calculations. So this is geodesic that is incomplete. And this means that, I mean, so there is one thing, for example, it could be wrong because again, you came to this coordinate singularity. But what is meant by geodesic incompleteness is mean that you have problems with extending geodesic, so to find the trajectory of this test body, but this problem cannot be cured by finding new coordinates or extending spacetime and so on. So it's not always easy to do for a practical, I mean, one choosing solutions to additional equations. It's not trivial, but this is the formal definition. So it's like a detection theory should say how the test bodies behave, and if we have problem with that, we try to cure them, but we cannot cure those problems, then this means that the space-time is really singular. And this is the formal definition. What was the history of the problem? Of course, everything started with the Einstein relativity in 1915, but the first, let's say, solution which told us something about singularities was the Schwarzschild solution, and it has been found as a solution. So they were not looking, Schwarzschild was not looking for a black hole, no, there is a Schwarzschild black hole, but he was looking for the shape of space-time around spherical stars. So he assumed, okay, I'm not interested what is inside. Later he found a so-called variable solution, but I'm interested that you have spherical star and what is above some surface. But formally, the solution we have found solves the Einstein equations even if you assume that there is no star. Yes, so you have like a spherical, non-trivial spherical space-time. But there are two singularities. One singularity is at the center, where R, the symmetry center, where R is equal to 0, and this is the true singularity. And the other singularity is at R equal to 2m, and this is just artifact of the wrong choice of coordinates. But they didn't know that at that time, and they didn't believe in the reality of the vacuum solution for like 50 years more. Then the other singularity that appeared was in the Friedmann paper in already in 1922. So he took this closed dust model and he saw what he has seen in the simplified description with these curves. Yes? So he said that there is a creation time. Okay, but these conclusions were not I mean, there were conclusions inside of this model without this Hawking and Penrose way of understanding things. Then there was the MET in 1927. So the MET, I mean, the cosmology started with Einstein's static universe, but there was a second model. So Einstein's static universe had cosmological constant and non-zero density of energy, but was static. There was another solution, the Sitter solution, that was vacuum solution, but was expanding. And Lemmet, he know that the universe is expanding already at that time, so he wanted to find a solution that shared both properties. I mean, he didn't like the Sitter solution because it was vacuum, and he said, I mean, something exists in the universe, so it shouldn't be vacuum. And he didn't like Einstein's solution because it was static, and he saw that the universe is expanding. So he wanted to find a mix. He asked if there is a mix of both solutions, and he found them. So it was 1927, but even more important was his paper from 1933. So what he did, you know, I told you that we have a very symmetric model with a very symmetric model with spatial and homogeneity and spatial isotropy. In fact, in general relativity, you could have space-time. What we get used to is that if something is isotropic, then it must be homogeneous. Or if something is homogeneous, maybe I should say that in this way it must be isotropic. But this is not true in general relativity. You could have space-time that are homogeneous, but not isotropic. In other direction, it's easier because if something is isotropic relative to every point, then it must be homogeneous. But you could have things that are homogeneous but not isotropic, like the vacuum, for example. Okay, so but what he tried, he assumed lower symmetry, just spherical symmetry around relative to one point. And he was studying dust solution. And so this is Lemmet-Tolman-Monti solution. It's known under this name now, but it was originally found by Lemmet. And he saw already something that in the Friedmann Robertson-Walker models, you could have big bang, and the big bang is at the initial moment that it's the same everywhere. Yes? But if you lose, if you will assume lower symmetry, just spherical symmetry around one point, the Big Bang is a function of radial coordinate. So it could happen at different times in different places in space. Okay, so it tells us that we have to be careful when we are studying this model, because if there is a small, like a small discrepancy between the symmetries, high symmetries we assume, and the real universe, there could be other things going, and the whole picture could be different. Okay, there was a okay, but there was he observed already in this 1933 that you can, in the same paper I think, that you can write space-time in the coordinates such that there are not singular at the horizon. And what is funny, it was even maybe not observed, but such coordinate system was used in 1924 by Eddington. But Eddington, he didn't realize that this is something important, so he didn't comment on that. He was using this non-singular system, but didn't recognize that it's so important. But Lemmet was, he knew that this is important. And then he tried another thing, he tried the Bianchi-1 space-time. So it's a space-time exactly of this type that is homogeneous but anisotropic. And he, in this paper, he had the conclusions that anisotropy can no more prevent the vanishing of space-time. So this means that even if you have a Big Bang, even if you lose the high symmetry of the solution. But this is according to the Bianchi solutions have another high symmetries, so it doesn't solve the whole problem, and we have to wait for Hawking to do that. Okay, and Chandrasekhar must and about that. So there were hints from other physics that when there is an electron, when you have something that you squash like white dwarf star and you make it too heavy, the matter cannot hold the pressure anymore and will collapse. Now we know to a neutron star, but then from neutron star we have the same limit. So there was hint from other physics that this collapse of the black hole could be a real thing. But Eddington, his authority, using his authority, just let's say cancel this this way of thinking, because he said that it's not possible, and Chandrasekhar was very young at that time, so he like slowed down the progress on black holes. And then you have Einstein in 1939. When he wrote the paper that the Schwarzschild singularities are not real, so you may see that he was reluctant to this idea that singularities in cosmology and singularities in black holes are real thing. But like it was May and July, so like 2 months later, there was the paper by Oppenheimer and Snyder, and in this paper they showed that the Schwarzschild solution could be obtained in the limit from regular initial data. So, and this is very important, that you have a setting that you know that it's physical. You switch on evolution within the theory, and the evolution, the equations tell you that you can have the particular end state that is similar to the Schwarzschild solution. So this a strong argument suggesting that maybe this final solution is a rough. But of course it was a spherical symmetry, to similar to the homogeneous and isotropy Big Bang. It cannot be trusted without more detailed analysis. And then in the 50s, Albert Einstein dies, and some people call it post-Einsteinian era. And it happened that, again, he died in April. In May already there was a first singularity theorem published by Choudhury. The story was, I will explain it very briefly in the next slide. But I mean, the people are initially confused. So if you know classical theory of fields, and you will find the first edition, I think, from 1960, you will find a chapter there, the absence of singularities in cosmological solution. So there was like a proof, they believe that they have proved that the cosmological singularity is not a real thing. This proof was not correct, so it was removed. And in your edition, you will not find it if you don't have this old edition. So the Penrose singularity theorem, Penrose was working maybe already from 50s or end of 50s on these things, but this first theorem was found in 1965. Okay, so it's based on some notions. I will explain it in the next slide. But it follows from this theorem that the singularities are not artifacts of the symmetries of special conditions. At least in this Oppenheimer Snyder, but in general, because the proof is mentioned. Okay, so now you may think how to do that, yes? How to prove that generic solution will develop a singularity if some conditions are satisfied. Because what I would try, I could like limit. I have one solution that is spherically symmetric, so maybe I take a axially symmetric solution and see if this happens. Maybe I will make some perturbations and so on and see if this will happen. But this is not sufficient. I mean, you have to find a tool that will tell you that this happened, provided some conditions are satisfied for any space-time. So you have to be smarter than that. And Penrose was. So you probably are familiar with the optical scalars. So when you have, okay, you observe something in astronomy, so the light is moving towards you on geodesic. So you can, for example, if you want to find the redshift, you can solve the geodesic equation, and you have this one light ray coming from, let's say, supernova to your eye. But this is not the whole information you are interested in, because maybe you want to calculate luminosity distance. So it's better to not study one geodesic, but let's say 1 million geodesics going from this supernova to your eye. You will see how the shape, you have like a congruence of geodesic coming from the source to your eye, and you can study how the shape of space-time along the way change the shape of this congruence. But of course, solving 1 million times geodesic equation for slightly different conditions is not very smart way. So you can derive the effective equations for that, in the sense that you are interested in some quantities of this congruence. And these quantities are like, cross-section of this thing. So you can think about the electric cable. The electric cable have a lot of small cables inside. Those are geodesics. And then you cut the cable and you see at given, let's say, instant of time, and you see what is the cross-section. And then you check later and it's growing or it's contracting. It could be deformed. It could rotate. So you have different optical scales. And this effective equation has this form, so it does not really matter what is written here, but it matters in the sign of the right-hand side. So here is the expansion scalar, here is the derivative of this thing along the geodesic, and here we have quantity that is positive with the minus sign, so this is negative, and here we have a quantity that the sign of this quantity is not clear. But if this will be non-negative, let's say, like this one, then this derivative will be equal to 0 or will be negative. And the expansion tells you how the cross-section, the area of the cross-section is changing. So here we have an example with the positive expansion. This is the time axis, this is one, and spatial direction was suppressed for simplicity. You see the positive this expansion, you have bigger cross-section. And the changes of that are controlled by this term. So what Penrose did, so here in this the first paper by Rachel on singularities, it was more on caustics, because now you have something that is this way. And I mean, in cosmology, you don't have to use this equation to light. You can use them to galaxies. I mean, they move along the geodesic and have some congruences of galaxies in the cosmic fluid. And then if there's like a focal caustic along the way, then it's similar to the squashing with the sphere of gas. So you can have some singularities. But the idea that came from Penrose was much smarter, because this analysis is totally local. You study infinitesimal neighborhood of the central geodesy. But Penrose did something like that, but global. So now you study so-called trapped surfaces. So imagine, you take here we have time axis, here we have a cross-section of space-time, so it's like some Riemannian space with those surfaces. You can think about this like the sphere around black hole, for example. And you have two families of outgoing geodesics, like normal to this hypersurface. So in fact, this is a sphere, not just a ring, but it's easier to draw it this way. And when the surface is not trapped, so the light rays going out of the surface could have negative expansion in one direction, but positive in another direction. But if it's trapped, so imagine the gravity is so strong that even those rays that you send outwards, I would say, they have negative expansion. Then you have a trapped surface. And this means, because light gives you some kind of a limiting behavior for test particles, that whatever was inside of this surface, it will be squeezed. Okay? And this is a condition that could be used to discover that there are, in a space-time, that there are singularities. So here you have original drawing from original figure from Penrose paper. So here is a so-called Cauchy surface of the, let's say, the state of the universe at some point. You have this, let's say, ball of dust, and it's matter, it's collapsing because of the gravity. And then here you have event horizon. And here you have this trapped surface. In fact, it's marginally outer trapped surface. So you can have many such surfaces, but we are interested in this most outer one. And this is a very useful thing that was not invented before. I mean, the Penrose invented it. But for example, when you study black holes, yes, and you study numerically black holes, then you want to know if you already have a black hole. So the thing that defines black hole is event horizon. But the event horizon, in order to find the event horizon, you have to know the whole evolution space-time. Why? Because imagine that, okay, there is a Schwarzschild black hole, and I'm not far from this black hole, but I think that I'm outside of the horizon. But there is a huge star falling into the black hole. So it could be, depending on the trajectory of the star, if it will fall or not to the black hole, that I will, because black hole will grow, that I'm already under the horizon because of the thing that will happen in the future. So it's not very practical because you would have to evolve till the end of the world your solution. But this trapped surface and this most outer one called apparent horizon is a very useful notion because on a given slice of the space-time, so in a given instant of time, in the space-time, you can find if it exists. If it exists, then this means that the horizon is somewhere, it could coincide with it, like for Schwarzschild, but it could be somewhere outside. I mean, it exists as well. So it's a notion that tells you that there could be a black hole. And this thing is collapsing. Here we see the photons going out from the trapped surface, but they finally hit singularity. And this figure is misleading in the sense that the singularity looks like a point here, but it's not true. You have to use different coordinates to see that the singularity is the event in space. For Schwarzschild, the space and time, they are exchanged inside of the vector. But it's a different topic, so I will not go into this. What is important for us? So there is a paper by Hawking and Ellis from 1965. Finally, I was not able to find this paper, but I found Stephen Hawking PhD thesis, because I was thinking if he wrote paper 1 year earlier, then for sure it had to be somehow included in his thesis. And here, if you can read, if not, I can read it for you. Okay. If the redshift of the quasi-stellar is quasar, I think it's odd name for quasar maybe, 309 is cosmological, then it will be beyond the point. There is a point that is important for this theorem. If you are living in Robertson-Walker time universe with normal matter, however, the assumptions of homogeneity and isotropy in the large seem to hold out to the distance of this quasar. Thus, there is a good reason to believe that our universe does in fact contain a closed trapped surface. And it should be pointed out that the possession of the closed trapped surface is a large-scale property that does not depend on exact local metric. Thus, a model that had local irregularities, rotation and shear, but was similar on the large scale at the present time to the Robertson-Walker model, would have a closed trapped surface. And now, so what he did, he found this kind of surfaces, but to understand that, what you have to do, you have to change direction of time. You know, if we imagine now that this direction of time is pointing downwards, then we are, the early universe is here, we are, let's say, here. We see trapped surfaces, but trapped in the reverse sense. So for Penrose, it was a future trap. For Hawking, it was a past trap thing. Then if your universe, you know that at your time, or let's say after a combination, some conditions were satisfied and as such trapped surfaces existed, then whatever the metric was before, it doesn't have to be Robertson-Walker, Friedmann, Robertson-Walker metric, whatever the metric was before, but if the some conditions were satisfied, then the universe to start in a singular state. So this is the content of this thesis. Okay, so there was this paper. The idea of the trapped surfaces came from Penrose. In fact, this is not a single theorem in the cosmological setting, but there's a series of theorems. You have different assumptions on that and different conclusions. I mean, conclusions are the same as singularity forms, but under different assumptions. Okay, so it's like many papers on this topic. So about apparent horizon, I already told you. Okay, so there is one more thing that has to be said here. So this Penrose singularity theorem says that if you have trapped surface in space-time, then the singularity will develop. But it doesn't tell you if you could have singularities without trapped surfaces. So you don't know if the implication goes in opposite direction. And in fact, nobody proved it in the general setting. So we have proofs for particular settings, but not in the general case. And it's called the cosmic censorship hypothesis. The hypothesis says that yes, if you have realistic collapse of physical matter, then you will have always, the singularities will always be covered by horizon. But this has not been proved. Penrose tried to do it, but so I think that there's Hawking once said that this cosmic censorship is almost proved because Penrose tried to disprove it and he failed. So but it doesn't count as a proper mathematical proof. And what is the condition? As you have seen here, this is the convergence condition. But when you use Einstein equations, then you can translate to the properties of the matter that fill the universe. Okay? And so, in the case of the singularity theorem from 1965, it translates directly to the thing that you have here, the so-called null energy conditions. But in other versions of the singularity theorems, the strong energy condition. So it's a bit different condition is being used. So in general relativity, you have many so-called energy conditions. What does it mean? It means that when you think about the right and left-hand side of Einstein equation is geometry. But when you think about right-hand side of the Einstein equations, then you have some matter fields there. And you cannot make it arbitrary. Because, first of all, the matter that we know in the real world behave according to some rules. So these rules have to be respected. But now, I mean, it's not, the problem is not so easy because when you think, for example, about early universe, then you don't know really how matter behave. How plasma behave in the early universe. So you don't know what is possible, so you don't know what exactly conditions should be assumed on the energy momentum tensor. So the situation is complicated, but you cannot neglect energy conditions. Because without energy conditions, an Einstein equation has no content. What do I mean by that? You have probably heard about the Sinch method of solving Einstein equations. So imagine that you take some kind of a geometry. So here you have a human figure. Okay? And this is a two-dimensional thing, but this thing could be moving. Okay? So you have one more dimension to that. So it's like a spatial geometry changing in time. Then you can plug it to the Einstein equation, use pi the metric that describes that, and numerically, I mean, you have it. Yes, if you was able to draw it, then you have it. Plug the thing here, put the thing here, calculate Einstein tensor, and then read out from the Einstein tensor via Einstein equations energy momentum tensor that describes that. And then you have the valid solutions to Einstein equations. So whatever you take, if you don't care about energy conditions, then it solves Einstein equations. And the theorem that doesn't give you any restrictions has no content. So this is what they mean by that. Without restrictions on the right-hand side, there is no content. Because the interesting theory says that something couldn't happen. Of course, so if you take the universe like that and you say that this is your cosmological model, then this could be disproved by observations. Probably, because you can always assume that we live on the forehead, let's say, and that the scale are so large that this thing is expanding. So you can make it hard to make this proof by observations. So the theory that doesn't give you the restrictions is not interesting. And general relativity doesn't give you restrictions if you do not assume something on the right-hand side of those equations. So those conditions are needed. Moreover, if you drop some of the conditions, there are like problems with causality, so you can have closed time curves. You can have these problems even if the energy conditions are satisfied. So there is like a, we believe that traveling in time, backwards in time, is not possible because we don't observe such things, and this is like a logical problem for us. So we throw away all the solutions that have this property. But even if you look at the curve solution, the black hole, you have seen the image of the curve, or real image made by astronomers. So if you take literally what is inside, then we have a closed time curves inside of curve. Okay, but as we understand it now, we do not worry with that because this is probably an artifact of this strict symmetry assumptions. And if somebody falls inside, and we do not treat it as test particle, but like something that carry energy, even small, then the structure changes and hopefully the closed time curve disappears. Okay, so, but the thing is with energy condition is problematic because if you do some kind of a quantum cosmologies, then you can have semi-classical approach. So you have classical space-time and quantum matter. And in the laboratory, you can show that there are some exotic states of quantum states that do not satisfy those energy conditions. The other thing is if you should treat them seriously at the astrophysical scales. Okay, so if you want to make a wormhole, then you need a lot of strange matter. And even if you have for a short instant of time in the laboratory or in some quantum experiment, it may be never possible to make astrophysical setting with this kind of matter. And if we will make it, we have some problems with that. So, and if you take a strong energy condition that is used in, I think, the most interesting singularity theorems, then it could be violated even by the cosmological constant, inflation, and some simple setting like scalar fields with appropriate potentials. But of course, I mean, on one hand, it's problematic. On the other hand, if you think about particular setting, like the singularity theorem applied to black holes, astrophysical black holes, then you don't have to worry with the cosmological constant in this setting, yes? Because the energy of that could be neglected for the black hole that is, let's say, planetary system size and solar system size, even if it is this huge hole. So your theorem works. Even if you look at the early universe with this cosmological constant, then the contribution of the cosmological constant compared to contribution of other forms of energy in the early universe is negligible. So you can still safely apply your theorems to that. But of course, the problem should be studied and understood better. And I think I will have time to say that. And this person, you know him as a brilliant theoretician, but he found a way to test those things. It's a joke, but I will show you at the end. But not really joke. It's just fun. Okay. And now, singularity theorems are very strong theorems, and they tell you much about the universe. But they tells you almost nothing about the structure of singularity. So you know that you will have some kind of an incomplete geodesics, but you don't know what will cause it from those theorems. Because, I mean, you can have incomplete geodesic because the curvature blows up, because you have a huge energy density of matter somewhere, okay? But you can have incomplete geodesic even in vacuum, and you can have even incomplete geodesic when you have, let's say, conical singularity, so all other points in space are fine, but you have just one point that it's wrong, and this is, again, like a singular space-time. So the question is, if you can learn using the fuel theorem, something about the generic about the nature of singularities. So here you will know the singularity very well, you can describe everything. But you can ask how generic is this behavior of space-time in the singularity. And people try to do that. So for example, if you will take literally the Friedmann Robertson-Walker models, and you can take the model that is expanding initially and then it's collapsing. So as I said, I mean, every model has its limitation. So you can ask, now we have evidence that the Friedmann Robertson-Walker models, they work well in the early universe. Let's say, I mean, we have like a consistent theorem. But if this collapsing model could be trusted at a late time, you don't know that. And it turns out that if you look at this model in the context of the full theory, the answer is probably no. There is a Belinsky-Kalatnikov-Lifshitz conjecture. And it tells you that when you have small, let's say, inhomogeneities in the collapsing matter, then they won't be wiped out in the collapse, but they will lead to a space-time that is very, not smooth, very, let's say, even chaotic in this situation. So it tells you that if you evaluate those simplified model, so the physical situation that we are interested in is this expanding universe and it's working. And we can show with the help of Hawking that it's fine. But if we would extend this analysis to the late times in the collapsing model, then it is not a good description, if the big hypothesis is correct. This is a conjecture. It has been proved, for example, in Goldie space-time. Sayed will talk about Goldie space-time today, later, I think. So it was proved by Richmond in a particular setting. In general, it's not proved, but we have some evidence that it's like that. So maybe it could be explained with the images. So this is again drawing by Roger Penrose. You see here you have this kind of a smooth thing, because it was like exactly spherical symmetry. But this is not how the things work in nature. It will be, the cloud is more similar to this thing. So the singularity here is like a crazy, and the space can behave in a very erratic way. Here, so it's not smooth and like this. This is what follows from the Bickel hypothesis, and it's based on some exact solutions where the proof could be given in an exact way, and numerical simulations in other settings. So here we have this Friedmann closed universe. This is again drawn by Roger Penrose. You see, you have this smooth Big Bang, but the end state, it's nothing that could be approximated by this model. Okay, so Penrose has different ideas related to this Bickel behavior. Why? Because it tells you that the initial singularity was very special. It was not generic if this hypothesis is valid, because it's not the time reversed version of this process. Okay, but this is a different story. So I think I'm almost done. Yes. So summary of my talk. So every theory has an application range. Every model within theory has an application range. We should remember about that. So not everything that what looks natural within the model. For example, you can take different fields that for which the energy conditions are not satisfied, and they look to work well in the model. But if you ask the following question, okay, but this is a model that is homogeneous and isotropic. But what would happen with this kind of matter if we will drop this assumption? And then, for example, you have like a plethora of strange things, wormholes in principle, or other things, naked singularities and so on, which we do not observe in the real universe. Then, if you use general relativity, it is used with energy conditions, then it has like a huge predictive power. Because Einstein had his equations. He was convinced that the universe is static, but the equations were saying, no, the universe is dynamic. And Einstein was wrong, the equations were right. Einstein equations said there are black holes. Einstein didn't believe them for a long time, but nowadays we know that Einstein was probably wrong, the equations was right. But if you will drop this, we know that general relativity predicts existence of black holes, predicts existence of the Big Bangs. Via singularity theorems, if the assumptions of these theorems are satisfied, so if some kind of energy conditions are satisfied by the matter in the universe. If you do the conditions, and as I told you, there are some arguments saying that maybe we shouldn't, in some situations maybe you shouldn't use them, but then the general relativity loses this predictive power. So then black holes could exist and are consistent with the theory, but are not predicted by the theory. We have to explain why they are there. So, I mean, for me, it's like the strict approach here is like a powerful thing, because I have theory that predicts things, and the things are being observed. And the astronomers did not observe so far any wormholes and other things that are consistent with Einstein equations if you will notice energy conditions. But of course, this is not like a clear thing, because sometimes you can construct a system that for which looks fine and the energy conditions are not satisfied. Okay, so how to test the energy conditions? Penrose has this idea, and he tested them a lot, longer time later, sometime later. Maybe you have heard this story already. So he had the following idea. He gave a birthday party, but he was almost alone. Somebody took his picture, because he sent invitations 1 day later. after the party. And this invitation, the idea is the following. The invitation was sent to people, but it's kept in Cambridge, as I understand. And it's visible for all the future scientists in Cambridge. And it will be there for a few hundred years, maybe. So if some of them will, let's say, will be able to construct a wormhole, if you have a wormhole, then it's almost easy to travel backwards in time, then they will come back to his party. And he tested this, nobody was there. So in some sense, he tested the knowledge of this future scientist. Of course, it will be that there will be, I don't know, a bomb will fall on Cambridge and this invitation will be destroyed. So it's not the proof, but he had this idea. Okay, I think I will finish here. It's exactly 15 minutes for questions. So thank you for attention.
Please, questions? Yes, thank you for a very nice talk. I have a couple of questions. So the first question is about this, I guess it's a Hawking singularity theorem about the singularity in the beginning of the universe. So I think he uses a strong energy condition, and as you said, well, we can also speak about inflating fields, but we have a cosmological constant which we have measured. So it doesn't mean that we have to retract this statement for now.
Okay, I don't know the microphone. You don't have to retract the statement because if you, okay, there is a cosmological constant, and in this particular setting, I think non-energy conditions were used, and they are not violated by the cosmological constant, but it doesn't matter, because if you go to the early universe, then density of radiation is so high that the cosmological constant is not important for the evolution. And what matters is, I mean, the whole stuff should satisfy this energy condition. So if you say that the cosmological constant violates strong energy conditions, you mean like an empty universe with a cosmological constant. Or the universe where the cosmological constant has dominant contribution. But if you have other stuff, then you shouldn't worry. So in case of the universe, you shouldn't worry about that. And in case of black holes, because the cosmological constant is not important for astrophysical black holes and these galactic huge black holes as well, you shouldn't worry about that. But you can worry about the conclusion about Big Bang, for example, if you have inflation, because then it's not clear if there was a Big Bang, because this theorem doesn't work. I mean, so as far as I know, people have some different versions of the theorems, but it's not definitely, I mean, you cannot neglect this convergence condition, and this is related to null or the strong energy conditions. So if you have inflation, then maybe you don't have a Big Bang.
Okay. And my second question is about Cauchy horizons. So in some singularity theorems, people say that they don't always point to singularities because a Cauchy horizon can simply terminate a curve, because the conclusion of these theorems, one of the conclusions could be that there's an inextendable future curve of some sort, and that the Cauchy horizon could stop it. But again, this usually is found in very specific solutions, symmetries. So again, the question is how likely they are in the real universe.
Oh, so I don't know the answer to this question. So there are like many versions of the singularity theorems. I mean, it's like not one thing, but they work already from 55 by Chaduri till late 70s, and I think the people are still working on that. So, but I don't know how to answer.
If I understood this question, it was just a confusion, because the term horizon is used at least in two different cases. One is event horizon, which deals with singularities, and the other one is Cauchy horizon, which has nothing to do with gravitation, deals only with solutions of some field equations in any space-time. This is just to use the same word. This is Cauchy Cauchy horizon, it means that if we have initial conditions, then we get solutions to the field equation, so we have determinism. We know what occurs after a short time. But it means that because these initial conditions usually are not given to the whole space, and in general relativity we don't know what is in fact in generality space, so we assume that it is only a part of something what we mean by space. This is the region where we have these initial conditions. But if you have something what is at the same time, but which is much more distant, then you can have a source of signal which enters in the future, and you don't take it into account, so you don't have a determinism. So in this sense, it is also in some sense a horizon, as because both works come from a geographical horizon, and this means that before or over horizon we can see something like in geography, or we can state whether the solution is deterministic, and under horizon is what we cannot predict because there may be some other solutions. Very easy. Suppose it is just in the form of a triangle, and the horizontal side of the triangle is the part of space where you give the initial conditions, and the two other sides, which are inclined under 45 degrees, are horizons. It means that whatever is in this horizon is determined by the initial conditions on this horizontal side, while what is beyond this the triangle is not determined by this initial conditions. Thanks.
Any questions? I have a question. I want to say some words about Penrose conformal cyclic cosmology and signals from before Big Bang.
Okay, so Penrose over the last, I don't know, 20 years probably, he developed the so-called conformal cyclic cosmology, and the main motivation behind that is the Weyl hypothesis. So if you see, the generic singularity is, I would say, simply crazy. It looks like this. So Penrose argued that the initial singularity, if it was described by the solutions, homogeneous isotropic solutions, then it was very special. It's not like every singularity. So in other words, if you have curvature, then it could be split to the gravitational degrees of freedom, the Weyl curvature, and the Ricci tensor is related to matter. So for some reasons, the Weyl tensor was exactly not like this. Here is one more, another thing, that the matter doesn't matter here. So this is crazy in terms of the gravitational degrees of freedom. And in this initial singularity, the gravitational degrees of freedom are 0. So the Penrose argues that the inflation was not needed because it's more complicated things than the initial condition follows from what was before. So you can think that some people think that they follows from if they were special or not, you should evaluate that within the theory that describes Big Bang, not within general relativity, because you cannot explain initial conditions for your equations within your equations. So they are taken from outside. But Penrose says that he found a way to do that. So our universe is not like this because it's expanding. So it started in this smooth thing, with the zero of the Weig tensor was expanding. And then if you think what will happen in the distant future, so the universe will be large. Some matter will fall into huge black holes, and this black holes will exist. But if there is a Hawking radiation, black holes will be smaller and smaller and smaller. Yeah, the Hawking radiation. If they evaporate at the end state, then you know when there is this relation derivative of the mass for the Hawking radiation, and it's like 1 over the mass, if I remember well. So it blows up at the end state. I mean, we don't not really know if it blows up in the sense of explosion because our equations are not valid yet. But in some semi-classical approximation, it behaves like that. So at the end state, those black holes simply could blow up. You can have some gravitational waves. Because of that, you have some gravitational waves because of the collisions of these huge black holes as well. But the universe expands and expands, I don't know how many billions of years. And then he assumed something like that, that in the end, all particles will be with, like, electric charge will be not conserved, all massive particles will decay, so you will have only radiation. And when you have a theory in which you have only radiation, in general relativity, the only conformal structure matters. So, and it doesn't make sense to describe this state of the universe using something that is not conformal. So, and then happens something that I don't understand, and I think he doesn't have, he has to invent equations for that because it's not the part of general relativity, like a conformal scanning. So the end of the universe, in which it's huge, but filled only with radiation, becomes the Big Bang. And the seeds for the homogeneities are these gravitational waves which were present there. And of course, to prove that, he is looking for some signature of these waves in the CMB, and there were different analyses. I mean, the CMB people say that it's not valid, but he says with his collaborations that they have found something. I don't know what is the final outcome. And I like this Weig hypothesis, this idea. I don't know about this conformal scanning. I don't have any opinion on that. It's like weird. But the Weig hypothesis is interesting.
One question, like I just wanted to understand: is there many differences between the type of singularities? Like, let's say if I have a star, if it collapses, I know that okay, at some point the geodesics will be incomplete. So one singularity here. So this is sort of in future. But if I go back in time, then I'm getting another geodesic incompleteness, which is the Big Bang singularity. So are there any more differences between these two singularities, or is one more local, the other more general? Or
so, I mean, there are differences. There was the whole classification of singularities made by Hitler in the 60s or 70s. So, for example, even if you think, I mean, the one thing is the real universe where we know singularities. We have the black holes with singularities, and we believe that it's settled down to the curve, and the Big Bang singularity, and it's described by the Friedmann. I mean, the singularity is not described, but when we are near the singularity, but Friedmann Robertson-Walker model. So the real singularities we encounter in the real world are just two types. But in principle, you can study many different singularities. For example, if we take Bianchi models, the models that are homogeneous but anisotropic, you can have like a several, I think it was figured by Tiptor maybe, or maybe already Tiptor. You can have several different types of singularities, like a Seeger, like I don't remember those names, no, but there is a classification. So in the real universe, I know two types, I would say, and in theory, you can have many different types of singularities. They could different things with you. For example, they can squeeze you to a point, but some of them just squeeze you in one direction and enlarge you in another direction. So you can look at the volume of the thing that it's falling to the singularity, what is happening with the volume sample. And it's quite interesting topic.
If I may add, so we can talk about the topology of these singular points.
Yes, we can talk about the topology, like the future, the past singularities topology. But well, why all these terms were was, well, we already have these measures like scalar curvature invariance, which should go up at the singularity. But then there are other singularities, like for example in Kerr black hole, which have a sort of directionality. When you take the limits from different directions, you get very similar effects, like in complex analysis you have with these branch heads. And then there are also conical singularities when you cut various spacetimes, put them together, and then there is a singularity, but you cannot really experience it. So that's why these theorems were introduced, to simplify the picture and give someone a coherent way to look at them.
And of course there are like conical singularities that could be hidden somewhere.
Any question?
So it's not about singularity.
Okay.
Thank you for very interesting lectures. So maybe I will have two questions. First, about black holes, and we know that in X-ray we have very strong iron line, and if we have small different cases where this line can arise in the inner part of accretion disk, and as a result, we can observe Doppler shift. So two different peaks, and also we can observe gravitational redshift due to the very, you know why. So which information we can obtain from analysis, for example, line width due to the gravitational redshift in for black hole physics, for example.
I mean, so these iron lines were somehow they fit to the image that this is a curved black hole. So I remember that this is like a proof of the curved black hole. And from the gravitational redshift, so we simply get the gravitational redshift. So I mean, you can check the consistency with the particular solution. But what other information I don't know. I mostly work in vacuum. I'm not an astronomer.
So my another question is about equation of state. So now we know some characteristic of dark matter and dark energy from CMB. So and we use different equation of state for describe this dark matter and dark energy when we resolve different cosmological equations. But how we can be, I forgot this in English thing. Okay, how we can know that this equation which we use we can also be used for early universe, because maybe we had another equation of state, for example, for dark energy, and all which we obtain now are not right.
Okay. So the short answer is that we don't know really what was the equation in the early universe. So my approach is that, I mean, you start with the Friedmann equations, as you have seen it. Then you have dust there, something with density but has zero pressure. And dark matter is a dust in this description. Then you have cosmological constant. And dark energy is a cosmological constant. And this is the standard thing. Okay? And now, if you think what happened in the early universe, I don't see a reason to do something with the cosmological constant, but some people don't like the cosmological constant, so they introduce scalar fields with that looks like a cosmological constant, but in fact have more complicated dynamics. The answer is that I'm fine with dark matter as dust and dark energy as a cosmological constant, but it could be something different. And what is the equation of state in the situation in the early universe? We don't have. I don't think we have some kind of evidence for that. So we don't know.
Any question? Please. Thank you for the nice talk. Is there any significance of velocity vector in FRW model? And sometimes it is taken as +1 and sometimes it is -1.
Sorry, could you repeat that?
Yeah. Is there any significance of taking a 4 velocity vector in FRW model? And sometimes we see it is +1 and sometimes it is -1.
But I don't know if I understand the question. 4 velocity vector
in FRW model.
Yes, but the vector that we have seen here, it was like, so one is the 4 velocity of the cosmic fluid, so it's not even here. That's
energy condition, mu.
Sorry?
In front where the strong energy conditions and all that, so there is R mu, that.
You mean here? So I use the same notation for different things. So here you have, this is null vector. So some people use K, is the wave vector here. But those equations are valid as well for timeline vectors. So for example, here in these energy conditions, this is defined for U being a null vector. And this is defined for U being a timeline vector. So I just use the same letter for different things. But anyway, I don't know if this answers your question or not really.
Yeah, I will discuss it.
So we can discuss this later, because I don't know.
My short question, maybe last. You didn't remember about big grip singularity. Where it is in your classification of
What kind of singularity?
big grip?
Big grip. Okay. So big grip is a hypothetical singularity, because if you here you have this equation of state. So here we have equation of state, and now we can think of something, some kind of matter in the universe that satisfies strong energy conditions. So it's look fine. I have seen a paper by John Barrow on this big grip. So usually people believe that you have to break some of energy conditions to have a big grip, but he showed in a paper that you don't have to. You can satisfy strong energy conditions and have some strange equation of state such that pressure blows up at some point. And this is like they call it a sudden singularity as well. So the universe exists, and then blows up. So I don't know if you are asking about Tipler classification for that. I don't know the detailed properties of that. I was not really interested because it needs like a non-standard equation of state to have something like that, I think. So I don't know if this answer. Thank you.